Welcome back, everybody. For today's deep dive, we are going to get to play around in a virtual physics lab.
Ooh, fun.
I know, right?
Hmm.
It's not something we get to do every day.
Yeah, I'm excited.
Me too. So we'll be looking at what's called a harmonic oscillator.
Okay.
And I think a lot of people hear that and think, oh, no, physics. But it's actually a lot cooler than it sounds.
Yeah, definitely. And harmonic oscillators are way more common than you might think.
Really?
Yeah. Like picture a pendulum swinging back and forth.
Okay.
Or like a guitar string
Okay, yeah.
vibrating after you pluck it.
Right.
Those are actually both examples of harmonic oscillators in action.
So they're like all around us?
Pretty much.
Wow. Okay. I did not know that.
Yeah.
But for those of us who need a little refresher, what exactly is a harmonic oscillator?
Sure. So basically, it's any system that when it's disturbed from its resting position,
Okay.
it wants to go back to that position.
Okay.
And it does it in a really predictable way.
So it always wants to go back to that like neutral position.
Exactly. And the key to that is something called a restoring force,
Okay.
which basically tries to pull that system back to that equilibrium. And the farther the system gets pushed away, the stronger that force is.
So is it kind of like a rubber band?
Yeah,
Like the more you stretch it, the more it wants to snap back?
exactly.
Yeah.
And that's what makes the motion all like rhythmic and predictable.
Okay. So that's like that restoring force is what creates that
Yeah.
pattern.
Exactly.
Cool. So for this deep dive, we're looking at a specific source.
Right.
It's called the Harmonic Oscillator Virtual Lab.
Catchy title.
I know, right? And it's from Open Educational Resources / Open Source Physics at Singapore.
Huh.
Have you heard of this website before?
Yeah, I think so.
They've got some cool stuff over there.
Yeah, definitely.
What's really neat about this particular source is that it's interactive.
Ooh.
So you don't just like read about it.
You get to play with it.
Yeah. You get to play with a harmonic oscillator.
That's awesome.
I know, right?
Way more fun than just reading.
Exactly. So what can you tell us about how this lab works?
Well, this particular lab lets you tweak some things,
Okay.
like the spring constant,
Spring constant.
which is basically how stiff the spring is.
Oh, okay.
And then you can see how all the changes you make affects the system.
Got it.
So it's a great way to understand all that physics underneath it all
Okay.
without having to get bogged down by all the complicated equations.
So it's like more about experimenting and seeing the results.
Yeah.
Rather than like getting lost in the math.
Exactly. I mean, the math is important, of course.
Right.
And it's there if you want to like dig into it.
Right.
But with this simulation, you can kind of grasp those concepts intuitively,
Yeah, okay.
which is a really good starting point.
I like that. It makes it way more approachable.
Yeah.
So looking at this simulation,
Yeah.
it looks like you can play with a bunch of different settings. We talked about the spring constant, but there's also the mass of the object that's attached to the spring, and there's even friction.
Cool.
So why is it important to be able to adjust the friction?
Well, in a perfect world,
Okay.
a harmonic oscillator would just keep moving forever.
Oh, wow.
But obviously,
That's not the real world.
that's not the real world. No.
Yeah,
There's always going to be some energy loss
right.
because of friction.
Uh-huh.
And that causes damping, where the oscillations gradually like decrease in amplitude
Okay.
until the system eventually just comes to a rest.
So it's like that classic playground swing example.
Oh, yeah.
Even if you give it a big push, it's eventually going to stop swinging.
Exactly.
Mm-hmm.
Because of the friction, like
Yeah.
in the chains
Yeah.
and air resistance.
And so this simulation lets you control that friction.
You got it.
So you can see how it affects everything.
Uh-huh.
That's so cool.
You could basically create a world where there's very little friction,
Oh, wow.
or a world where everything comes to a stop super quickly.
That's awesome. I'm starting to see how this simulation can really bring the concepts to life. And I also noticed something interesting. The source mentioned that you can adjust the equilibrium position. What
Right.
does that mean? And why is that significant?
So the equilibrium position is basically the resting point of the system.
Okay.
So imagine a spring that's hanging vertically with a weight attached to it.
Okay.
The equilibrium position is where the weight naturally hangs when it's not being messed with.
Okay.
Now, what's cool here is that the simulation lets you actually change that resting point.
Wow.
You can shift where the system wants to settle.
So instead of just letting the spring hang naturally, you could like attach the other end to a motor or something and make
Yeah.
it move up and down.
Exactly.
So you're changing where that equilibrium point is.
You got it.
Whoa. Okay, so you're basically like moving the goalposts while the game is still going on.
That's a great way to put it.
Okay, that makes a lot of sense.
Yeah.
So I'm already starting to see how much you can explore with this virtual lab.
Me too.
We've covered some of the basic features and how they relate to the real world.
Yeah.
But I'm ready to dive deeper.
Okay.
What else can we learn from this simulation?
One of the most important concepts in physics is energy.
Right.
And this simulation is a really fantastic way to see how energy works in a harmonic oscillator system.
Perfect. Let's jump into that next.
Sounds good.
Okay, so we're back and we're ready to talk about energy,
Yeah,
which is a pretty big deal in physics.
it is.
I remember learning about things like potential energy
Right.
and kinetic energy, but honestly, it always felt kind of abstract to me.
Sure.
So how does this simulation help to make those concepts more concrete?
Well, as that object on the string
Okay.
is moving back and forth,
Uh-huh.
its energy is constantly shifting between those two forms,
Okay.
potential and kinetic.
Gotcha.
So potential energy is stored energy. It's like when you stretch a rubber band.
Okay.
Kinetic energy is the energy of motion.
So like when that rubber band snaps back?
Exactly.
Gotcha. Okay, so if we're looking at our virtual spring and block,
Yeah.
where would that potential energy be the highest?
Okay, so think about when that spring is stretched or compressed, like to its maximum.
Okay.
At those points, the block is momentarily at rest,
Uh-huh.
and all that energy is stored in the spring,
Okay.
ready to be released. So that's maximum potential energy.
So at that point, kinetic energy would be zero.
Exactly, because it's not moving.
Right, because it's not moving.
Yeah, and then as that spring pulls the block back towards that equilibrium position,
Okay.
all that potential energy starts converting into kinetic energy.
Okay.
So the block speeds up,
Right.
gaining momentum.
So it's like a trade-off.
Yeah.
As that potential energy decreases, kinetic energy increases.
Precisely. And when the block passes through that equilibrium point,
Mm-hmm.
the spring is neither stretched nor compressed.
Okay.
So all that potential energy has been transformed into kinetic energy.
Gotcha.
So the block is moving at its fastest.
Okay. I'm following so far, but then what happens?
Well, as the block keeps moving,
Okay.
it overshoots the equilibrium point,
Uh-huh.
and the spring starts stretching or compressing again in the other direction.
Oh, okay.
And now the kinetic energy starts converting back into potential energy.
Gotcha.
The block slows down, eventually coming to a stop at the opposite extreme.
Hmm.
And then the whole process repeats
So it's a constant cycle of
Yeah.
transforming that energy back and forth.
between potential and kinetic,
Yeah.
like a never-ending dance.
I like that. Never-ending dance.
Yeah, and in an ideal system where there's no friction,
Right.
this dance would go on forever.
Oh, wow.
The total energy would stay the same,
Okay.
just shifting back and forth between these two forms.
But as we talked about earlier, friction kind of throws a wrench into things, right?
Exactly. Friction causes some of that energy to be lost.
Uh-huh.
Usually it dissipates as heat.
Okay.
So instead of oscillating forever, the system gradually loses energy,
Right.
and those oscillations get smaller and smaller until the block eventually just comes to a stop.
At the equilibrium point.
Yeah.
So this simulation actually lets you see that energy being lost
Huh?
due to friction,
Right.
which is pretty neat.
Yeah, and you can experiment with different levels of friction
Oh, cool.
to see how it affects that damping process,
Okay.
like how quickly that energy dissipates.
This whole concept of energy transformation and conservation,
Yeah,
it's something we see all around us, right?
it is.
Not just in a physics lab.
Yeah, it's everywhere.
It's amazing how this simple model can show us such a fundamental principle.
It really is.
I remember learning about something called the period of oscillation,
Right.
which is basically like the time it takes
Yeah.
for one full cycle of motion.
Uh,
So does the simulation let you explore that concept as well?
it does. And one of the key things to understand about a harmonic oscillator
Okay.
is how the period is affected by different factors,
Okay.
like the things we've been talking about, like the spring constant, the mass, and the friction.
Gotcha.
All of those play a role in determining that period.
Okay, so walk me through this.
Okay.
Let's start with the spring constant.
Okay.
So if you make the spring stiffer,
Mm-hmm.
does that make the period longer or shorter?
So a stiffer spring means a higher spring constant,
Okay.
and that leads to a shorter period.
Okay, so it would be faster.
Yeah, it's like having a stronger rubber band.
Yeah.
It snaps back more quickly.
Right.
So those oscillations are faster.
That makes sense. What about the mass? How does that affect the period?
Think about it this way. A heavier object takes more force to get moving.
Okay, yeah.
So a heavier mass will have a longer period.
Okay.
The oscillations will be slower.
So a lighter mass would have a shorter period.
Exactly.
Yeah.
And the great thing about this simulation is that you can adjust all those parameters.
Right.
You can adjust the mass, the spring constant, even the friction,
Uh-huh.
and actually see how those changes affect the period of oscillation.
It's like a playground for physics concepts.
It is.
You get to experiment and see those relationships firsthand.
Yeah, you take something that can feel really abstract,
Right.
like equations on a page,
Yeah.
and you turn it into a real experience.
A tangible experience.
Yeah.
Okay, cool. So we've been talking about the simulation itself.
Yeah.
But I noticed the source material also links out to some other resources,
Oh, right.
like a blog post
Okay.
and some additional references. So
Right.
what can we find in those?
The blog post goes into a little more mathematical detail
Okay.
about the equations that govern harmonic oscillators.
Oh, cool.
So if you're interested in like the underlying math,
Right.
that's a great place to explore further.
So for those people who really want to get into the nitty-gritty,
Yeah, exactly.
what about those other references?
Those provide a lot more context
Okay.
and examples of harmonic oscillators in different areas of physics.
Okay.
So you'll see that this concept isn't just limited to springs and blocks.
Right.
It pops up in all sorts of unexpected places.
Yeah. So it's a reminder that the principles we're exploring here
Yeah.
have applications that go way beyond this specific virtual lab.
Yeah, it's something fundamental about how the world works.
Exactly. Okay, so that's pretty cool. We've talked about energy transformation, damping period, and even some of the broader implications of this model.
Yeah.
What other insights can we glean from this deep dive?
I think it's important to highlight the pedagogical value of this resource.
Okay, so you're saying it's more than just a cool simulation to play with.
Definitely, yeah.
Yeah.
It's a powerful tool for teaching and learning about harmonic motion.
So it's like a legitimate educational tool.
It is. The interactive nature of the lab,
Yeah.
combined with those clear explanations and supporting materials,
Right.
makes it a fantastic resource for anyone who wants to understand this concept more deeply. It's so much more engaging and intuitive than traditional textbooks or lectures.
Yeah, it's true. Being able to experiment and see those results in real time,
Yeah,
that's a game changer.
it really is.
Like it allows students to take ownership of their learning. They
Exactly.
can experiment. They can make mistakes. They can
Right.
learn from those mistakes,
Yeah,
which you can't really do with like passive learning methods.
right. It's like the difference between reading about how to ride a bike
Yeah,
and actually getting on one and figuring it out for yourself.
I like that analogy. Okay, so what you're saying is this virtual lab is really exciting.
It is.
It makes physics come alive.
It does.
It encourages exploration.
Yeah.
And it helps people to really appreciate how things work.
Exactly.
Well, we've covered a lot of ground in this deep dive so far.
We have.
You know, we've explored the simulation, we've broken down those concepts like energy and period,
Right.
and we even touched on the broader educational value of this resource.
We did.
But before we wrap up, I'm sure you have one of your thought-provoking questions
I do.
to leave our listeners with. So what is it this time? All right, lay it on me. What's that question?
Okay, so here's something to think about.
Yeah.
How could you use this simulation to investigate the relationship
Okay.
between the period of oscillation
Mm-hmm.
and the mass of that block?
Mm.
So what kind of experiment could you design within that virtual lab?
Yeah.
And what results would you expect to see based on what we've been talking about?
Whoa, okay, that's a good one. That's really going to make everyone think.
Yeah, it's a challenge
Yeah.
to our listeners.
Yeah, to really engage with the simulation
Mhm.
and put their understanding to the test.
Exactly. I mean, it's one thing to hear us talk about these concepts,
Right.
but it's a whole other thing to actually like experiment with them firsthand
Yeah, for sure.
and see those relationships play out.
Yeah, so to all our listeners out there, I encourage you fire up that virtual lab
Yeah.
and give it a try. See if you can design an experiment to explore how changing the mass of the block affects that period of oscillation.
And don't be afraid to get creative.
Yeah.
Try different combinations of parameters. See what happens when you increase the mass,
Yeah.
decrease the spring constant,
Okay.
or add some friction into the mix.
The beauty of the simulation is you can explore all these scenarios
Yeah,
without any like real world consequences.
totally.
It's a safe space to play and experiment and learn.
Exactly. And as you're experimenting, think about what's happening on a deeper level.
Okay.
Like, why does changing the mass affect the period in that way?
Right.
Connect those observations back to the concepts we've been talking about.
Right.
Things like potential energy, kinetic energy, and that restoring force.
I love how this simulation really encourages you to think.
You too.
It's not just about like memorizing facts.
Right.
It's about understanding those underlying principles
Exactly.
and seeing those principles in action.
It's about developing an intuition
Mm.
for how things work.
Okay. Yeah, I like that aha moment.
Yeah, when it all clicks.
Yes. Okay, well, I think we've covered a lot of ground today.
I think so too.
We explored the Harmonic Oscillator virtual lab. We talked about energy transformation damping and period.
Right.
And we even touched on like the broader educational value of this resource.
Yeah, and we challenged our
We
listeners
did.
to keep exploring
Yes.
on their own, to design their own experiments and come to
Yeah.
their own conclusion.
Because at the end of the day, the best learning happens
Yeah.
when you're actively engaged,
Oh.
when you're curious,
Yeah.
and when you're willing to experiment.
So to all our listeners out there,
Yeah.
keep exploring, keep learning, and keep those knowledge-seeking vibes high.
Love it. We'll catch you on the next deep dive.